Okay, so today we're talking about nuclear decay, nuclear stability. Okay. This is a nice wrap up to the end of the semester, because if you remember, the very first thing we did in this class, the very first thing we did was kinetics, right? Rate of reaction. How fast does a reaction occur? And we used our integrated rate laws, right? We talked about how do you get a straight line, what do you plot to get a straight line, all that good stuff. We had zero order, first order, second order, right? That was the very first thing we did way back in January. It seems like it was just yesterday, right? Well, radioactive decay follows first order kinetics. So that means that the integrated rate laws for first order reactions, we can use those to do calculations for nuclear decay, okay? So if we're looking at nuclear decay, it's following first order kinetics. So all the integrated rate laws we learned for first order kinetics apply to radioactive decay, which is nice because we learned that back in January. Remember from January, the only difference was we used the letter A instead of the letter N, right? It was natural log of A and natural log of A sub 0. Here we're just using N. Who cares? You can call it X for all I care, right? There's the linear version. This is the slope-intercept form version. And this one's not in slope-intercept form. You can use either one of these, right? And this is the half-life equation. K is the rate constant, right? What does this 0 stand for? This 0 stands for initial, right? So this would be the initial mass, and this would be the mass at time t, right? This would be the initial mass, this would be the mass at time t. That's the rate constant. And I will give you the formulas. You just have to be able to do the arithmetic, because these formulas will all be on your reference page on your final exam. Okay? And all nuclides are going to have unique half-lives. That's unique to each nuclide. So don't assume that one is going to work for all of them. Right? That's why we do kinetic calculations for every nuclide. So let's do this one together. What's the half-life of technetium 99 if its rate constant is 0.116 hours inverse? So all we're doing is using the half-life equation, right? We're just plugging into the first order integrated rate law half-life equation. Remember, half-life is a unit of time, and so we're using the half-life equation for first order kinetics, right? So natural log of 2 over K, there's its rate constant. So since this is in hours inverse, my half-life will be in units of hours, right? 3 sig figs, 3 sig figs. All right, so why don't you try this one? What's the rate constant for the nuclear decay of thorium-234 if its half-life is 24.1 days? Take a second and try that one. All right, so we're plugging into first order integrated rate law half-life equation, right? Because my unit here was in days, right? Then our rate constant would have units of days inverse, right? Now, if you're doing a homework problem and it asks you for the rate constant to be in a specific unit, then you would just convert it to whatever that unit needs to be. Do we agree on how to do this one? Did you get the same number I got? 3 sig figs? All right, let's do this one. If the half-life of molybdenum 99 is 66 hours, what mass of a 1 milligram sample will remain after 330 hours? So this is going to be a two-step problem. This is going to require us to do two different calculations, because I've given you half-life, and I've given you some initial mass, and I've given you some unit of time that has elapsed. And I want to know how much of that mass will remain. What piece of the puzzle is missing? K, right? We have to calculate K first. How will we get K? From the half-life equation, right? So you've got to calculate K first from half-life. And then we'll plug it into our integrated rate law. Okay, this is a two-step problem. because I didn't give you the rate constant. So you've got to use the fact that I've given you its half-life to calculate K, and then we'll plug into the integrated rate law. Now you can use this version, or you can use the slope-intercept form version, whichever version makes you happy. Right? You'll get the same answer either way. Does everyone see why this is a two-step problem? So I didn't give you the rate constant. So you've got to calculate it first, and then solve for my mass at time t. One thing to watch out for, make sure that your half-life time matches the time that has elapsed, right? If I give you the half-life in seconds and ask for mass that remains after days, you need to convert days to seconds or seconds to days, right? Because these two units must be compatible. Otherwise, your answer is going to be garbage. So first we calculate K using the half-life equation. So 66 hours is the half-life. So I got 0.0105 hours inverse as my K. Everyone see how we did that? Just natural log of 2 divided by the half-life. Now I can plug in and solve for the second piece of the puzzle, which is N, right? This is N sub 0. That's the initial mass. That's 1. This is what we're solving for. So we do some arithmetic. Natural log of x over, and 1 over x is equal to K, which I just solved for, times time, which is 330, right? Hours and hours. So hours inverse and hours cancel. So this becomes unitless. How do I get rid of the natural log? Raise both sides to the e, right? So 1 over n is equal to e to the 3.47, which is approximately 32. So n would be 1 over 32.0313 milligrams. Does that make sense? Is that a reasonable answer? Would you expect the mass to go down? Yes, if your mass somehow goes up, something's wrong, right? Because this is nuclear decay. This is nuclear decay. I didn't tell you what kind of decay it is, if it's alpha decay or whatever, right? We're just saying it's decay. We're not worrying about the decay reaction right now. We're just saying it's breaking down, right? So that means that this mass is going to be going down. If somehow your mass goes up, you've either solved for the wrong variable or you did some wrong math. Now, what if I gave you the mass and said, what was the original mass? Could you solve for that? Sure, you'd just be solving for this variable instead. So why don't you try this one? If the half-life of polonium-210 is 138.4 days, how much of a 1.5 milligram sample remains after 2 weeks? Try that one. All right, let's see what we came up with. So we've got days and weeks, right? So either you need to convert days to weeks or weeks to days, right? Because if my unit of half-life is in days and the time elapsed is in weeks and I don't make that conversion, my answer is going to make no sense, right? So either convert days to weeks or weeks to days. It doesn't matter to me which one you pick. So first we've got to calculate the rate constant, right? Because I didn't give you the rate constant, I just gave you the half-life. So using the half-life to calculate the rate constant, I came up with 5 times 10 to the negative third days inverse. I kept mine in days. Do we agree with K? If you kept yours in days, if you converted days to weeks, your answer would obviously be different. Do we agree? We kept it in K. K in days. Now we'll solve for the mass after 2 weeks have elapsed. 2 weeks would be 14 days, right? So I got 1.4 milligrams. Does that make sense? Started at 1.5, it only went down to 1.4. Well, has a full half-life gone by yet? No, remember, half-life is the time it takes the sample to go down by what? 50%, right? A full half-life hasn't gone by yet. Only 14 days has gone by. So does it make sense that my mass only went down by 0.1? Yeah, because only 14 days have gone by. I haven't even made it to one half-life yet. I haven't even made it half of one half-life yet. So yeah, that's a reasonable answer. Do we agree on this one? All right, why don't you try this problem? The half-life of lead-214 is 26.8 minutes. After 4.5 days, a sample has a mass of 3.31 grams. What was the original mass of the sample? See if you can do that one. Okay, let's see what you got for this one. So, again, I've given you half-life in minutes and time elapsed is in days. So you're going to need to decide which unit of time you want to go with, either convert days to minutes or minutes to days. Something's got to be converted here, right, so that these two units match each other. And this time we're solving for the original mass. So would we expect our number to be greater than or less than 3.31? If we're solving for the original mass, should that number be bigger or smaller than this?
Bigger.
Bigger, and a lot bigger, right? Because it's got a half-life of about every half hour. It's going down by half, right? And 4.5 days have gone by. So you would expect that original mass to be a lot bigger than 3.31. But before we can do anything, we have to calculate the rate constant, because I didn't give you that. So for the rate constant, I kept everything in minutes. That's what I did. So there's my rate constant in minutes, 0.0259. And then I converted days to minutes. So 4.5 days is 6,480 minutes. So I got 2.56 times 10 to the 73rd grams. Did you get something similar? Does that make sense? Is that a reasonable answer? Well, yeah, every half hour, the mass of this thing goes down by half, right? And we've been watching it for 4.5 days. And we've got 3.31. So we should have begun with a huge amount if we've still got 3.31 grams. And every half hour, approximately, it's being cut in half. So yes, that's a reasonable answer. So everyone see how to do this one. This time we're solving for the initial mass. All right, here's another problem that you could be asked. How long will it take for 25% of the carbon-14 atoms in a sample to decay? The half-life for carbon-14 is 5,730 years. So this time I'm asking, okay, if I begin with a sample, how long is it going to take for 25% of it to go away? Not 50%, because if I said how long will it take 50%, well, that's the half-life. You could solve for that pretty easily. But I'm not interested in that. I'm interested in how long will it take 25%. So this is this problem. We're going to use first-order integrated rate law as well. So first we're going to calculate the rate constant. Got to do that, right? Can't do anything without the rate constant. So that's step one. And now we're going to pretend that we're beginning with a 100-gram sample. Just makes my math nice and easy. Okay, so you can assume what your initial mass is wherever you want it to be. I'm picking 100 just to make things nice and easy. So that means my initial mass is 100. If 25% of it decays, well, that means that 75 grams remain, right? Because what's 25% of 100? 25 grams, right? So 25 grams go away. That means 75 grams are left. So n sub 0, the initial mass is 100. N is now 75. Does everyone see how we made these two numbers appear? We're pretending we started with a 100-gram sample because I didn't tell you what the initial mass is, right? I just said pretend. Now, if I gave you the initial mass, let's say the initial mass was 4.3 milligrams. Well, then 4.3 would be here, and then you'd subtract 25% of that to go here. Right? But I didn't tell you the initial mass, so that's why you just picked 100 arbitrarily. And we just plug into our integrated rate law. Does this make sense? So everyone see where the 100 and the 75 came from. Again, if I had given you the initial mass, that would be what goes here, and then you subtract 25%, and that would be what goes here. But since I didn't give you any initial mass, you're just pretending you start with 100 because that makes the math a little bit easier. And then we just solve using the method we've already discussed, right? Solve for K, and then initial mass is 100, mass at time in the future is 75, so natural log of 100 over 75 is equal to K times T. T is what we're solving for, right? Time. So 2,378 years. It's a long time. But keep in mind, how long is the half-life? The half-life is 5,730 years. So is that a reasonable answer? We haven't even made it to one half-life yet. So yeah, that's a reasonable answer. You guys ready to try one? In a sample of californium-245, how long will it take for 70% of the original mass to decay if the half-life is 45 minutes? All right, let's go over this one. Half-life is 45 minutes, so it's not going to take very long for 70% of it to go away, is it? 45-minute half-life. We're going to calculate K, and then we're going to solve for the time. I got 78 minutes. Did you? More than one half-life has gone by, right? We've made it past one half-life. We're at 70% remaining. Any questions on how to do this one? I mean, 70% gone, not 70% remaining. All right, a new element is discovered. It's named after me, of course. Why not? If bronchium has a half-life of 41 hours and 18 minutes, how long will it take for a sample to decrease by 15%? All right, let's see about bronchium. Now, just a reminder, I haven't given you any particular initial mass. But what if I did give you an initial mass, let's say of, I don't know, 27 grams? Could you still solve this problem? Because 27 would be your initial mass. How would you get your mass at time t? You'd take 15% of 27, right? And just subtract. Okay? So you can do this even if I don't give you, even if I do give you the initial mass. All right, so for rate constant, that's what I got, 2.797 times 10 to the negative fourth minutes inverse. I kept everything in minutes. Assuming 100 gram sample, so that means if 15% is gone, I've got 85 grams remaining. So that would be 581 minutes, or if you kept yours in hours, 9.7 hours. Do we agree? Did you get something similar? Depending on how many decimal places you carry in your natural log and this part. All right, here's a third type of decay problem. A wooden artifact has carbon-14 activity of 9.1 disintegrations per second. Right? So every second, 9.1 disintegrations are occurring. If the carbon-14 activity of the same mass of freshly cut wood, right? So this is old, and this is new wood, is 15.2 disintegrations per second. How old is the artifact? So that's what we're going to do here. And again, you need to know the half-life. Half-life is 5,715 years. So we're comparing an old artifact to a sample that we have of modern, right? So that we can see, okay, how much is the rate changing? And then we can figure out how old it is. So we're going to use, instead of concentration, right, we're using activity here, because remember we used A last semester, in the beginning of the semester, now we're just using activities here. So natural log of the artifact over natural of the activity in the fresh is equal to negative KT. Okay? And of course, before we can do any of that, we got to get K, right? Because we have to have K. So we get K. Natural log of 2 is approximately 0.693. And this is the half-life I was given. So the natural log, this is the old artifact. This is the current sample, right? So old over current is equal to K times T. And we're solving for T. Okay, natural log of old over modern is equal to K times T. Negative, don't forget the negative there. So we do a little bit of rearranging, and we get 4,240 years. This is using the linear version of the integrated rate law, the slope-intercept form. Think about this one. Make sure you understand how we got this number. Does everyone see how we arrived at 4,240 years? Old over new. We're using the slope-intercept form. We're using the y equals mx plus b form. You ready to try one? You need another second. All right, so why don't you try this one? Clay artifact, carbon-14 dating. The artifact is at 3.4 disintegrations per second, and the same mass of modern clay is 9.9 disintegrations per second. What's the age of this artifact if the half-life is still 5,715 years, right? That's not going to change because each nuclide's half-life is a constant. So how old is this piece of clay? Okay, so we're comparing our artifact to modern. So we've got to solve for the rate constant, right? We can't do anything without that. So the natural log of 3.4 divided by 9.9 is equal to negative k times t. T is what we're solving for. So I got 8,833. So when we round that to sig figs, that would be 8.8 times 10 to the third. Do we agree? Do you get something similar? Any questions on how we obtain this answer? All right, let's talk about mass defect. So mass defect is the difference between the actual mass, so when you actually measure it, and what you expect the mass to be, okay? So what you expect the mass to be would be determined by taking the mass of a proton, for instance for hydrogen, plus the mass of an electron, right? Because proton and electron, that gives you a hydrogen atom. So that, you add those two up, that's what you expect the mass of hydrogen to be, and then you determine what that mass of hydrogen actually is, right? And so that difference between them is the mass defect. So let's do this one together. There's an isotope of fluorine, fluorine-19, right? And that means that this isotope is 9 protons and 10 neutrons. Remember back to the very beginning of Chem 1, right? Subtracting these two gives me number of neutrons, 9 protons. And so I'd have to give you the measured mass, okay? You experimentally determine the mass of this isotope to be 18.99840 atomic mass units. That's what you determine it to be experimentally. Now here's what you know a proton weighs. Each proton has a mass of 1.00 AMUs, and each neutron has a mass of 1.008 AMU. Multiply this by 9, multiply this by 10, and add them up. So this is what I expect the mass of this isotope to be. Here's what I measure the mass of the isotope to be. So the mass defect is just the difference between them. Okay? That's how we calculate this. So I would have to give you the measured mass, and I would tell you the mass of a proton. I'm not going to make you memorize the mass of a proton and the mass of a neutron. That's just wasted brain space, okay? So if I were going to ask you a problem like this, if you're doing it on the homework, you could look it up in your notes or online, right? But if it were on a test, I would tell you the mass of a proton. You would just need to figure out how many protons and neutrons you have, right? So you can know what numbers to multiply these by. Does everyone see how to do this? It's the difference between what you expect the isotope's mass to be and what it actually comes out to be. So why don't you try this one? The measured mass of oxygen 16 is 15.994. And there's the mass of a proton, there's the mass of a neutron. What's the mass defect here? Okay, mass defect here. Again, I would have to give you the measured mass, and I would give you the mass of a proton and the mass of a neutron. I'm not going to make you memorize that. But it is up to you to remember how to figure out how many protons and neutrons you have to deal with. So I got a mass defect of 0.13252 atomic mass units. Do we agree? The difference between what you expect the mass to be and what the actual mass is. Okay, let's talk about nuclear stability. Nuclear stability. All elements greater than molar mass and atomic number 83, they're all going to be radioactive. And so let's talk about nuclear stability plot. So what this is a plot of the number of neutrons versus the number of protons for the stable nuclides. It's going to look something like this, right? So this is protons versus neutrons. The 1-to-1 ratio is here, and then here's what a lot of your plots end up looking like. And so based on where your neutron to proton ratio ends up being, this will allow you to predict what kind of decay your isotope's going to undergo. And so if you are above that band, which we call the belt of stability, you're going to undergo beta decay. Beta decay. So again, you're calculating the neutron to proton ratio, right? So the neutron, and this is what 1-to-1 looks like, neutron to proton ratio. If it puts you up here above, this will allow you to predict you're going to undergo beta decay. And if you're below, you're either going to undergo positron emission or electron capture. Right? So you can predict the kind of decay your isotope will undergo based on where it ends up on this chart. Again, we're plotting, we're calculating neutrons over protons. What's the ratio? Where are you? Are you above or below that band of stability? All right, that was all decay, right? Let's look at fission really quickly. Fission is different from fusion, right? Fission and fusion are not the same thing. So we've got an unstable nucleus, we've got a lot of energy. And so here's a chain reaction, a fission chain reaction, right? So you've got this occurring, and then this occurring, and then this occurring, and it's just a chain reaction, right? So each one of these is releasing a lot of energy. And that's about how far we're going to get into that. You can take physics classes on fission calculations. We're not going to do that. So when we talk about the synthetic elements, right, we've recently updated our periodic table. How do we get those? Through synthetic nuclear reactions. Synthetic just means man-made. And so what we do is you take your atom and you just bombard it with more subatomic particles, protons and neutrons, or even bigger atoms altogether. And so this is not something you want to do in your basement, right? Because you're going to get gamma radiation. That would kill you pretty quickly. Not something I recommend doing at home. Probably going to get some federal authorities showing up at your house too. And so here's an example of radioactive phosphorus. So you're producing this gamma radiation here. And the transuranium elements, so these are the guys over here on the periodic table, right? These guys, transuranium elements, those were all produced by that same synthesis. Right, so there's Sborgium, in case you were curious what he looks like. All right, let's talk about how to protect yourself. If you do want to go be a nuclear chemist, how do you protect yourself? So if you're trying to protect yourself from an alpha particle, what's an alpha particle? The same thing as a helium atom, right? So if you're doing something that's producing helium atoms, piece of paper, you're good to go, right? Beta particles, you need to protect yourself using lead, centimeter. Gamma, you need at least 10 centimeters of lead, right? Gamma radiation is obviously the worst of these three, followed by beta, followed by alpha. Okay. And if you are ever around radiation, you're studying radiation, you're doing radiation tests, you'll wear a dosimeter. I actually worked as an intern and with a radioisotopes lab, and I wore a dosimeter and I turned it in at the end of every week, and it measured how much radiation I was exposed to. And so if you are a person who's working in that kind of lab, you'll wear one too, so you can see how much you're being exposed to, right? Because you don't want these things to happen. That would be bad. And some sources of radiation. I mean, a lot of people don't realize that you're being exposed to radiation just from your house, being outside, going on a flight, right? So there's diagnostic X-ray, right? That's 50, that's milligrams though. But I mean, you've got naturally occurring radiation from the earth, building materials, what you're breathing in, naturally occurring, right? And these are all millirems, okay? Not rems, millirems. Artificial sources are actually pretty low, right? So if you live near a nuclear power plant, you're not going to go in the dark, because that's a whole lot less than what you get just from the earth itself. Radiation also increases with altitude, found in the ground, building materials. Radon is a large contributor, and we see about 15% attributing to the lung cancer development from people who are healthy, who have no smoking, right? You hear of people who've never smoked a day in their life and they get lung cancer. A lot of times it can be attributed to radon exposure. Yeah?
Astronauts in space, are they protected by the Earth from science radiation or no?
They would have to be really careful about when they're outside.
So they're protected when they're inside?
When they're in their shuttle thing,
Okay.
they would have to have some sort of protection from that, yeah. Yeah. And then because radiation is occurring everywhere, I mean, that's how you can get radio dating, right? Because you're intaking this from your environment. Here's a picture of radon distribution across the country. So what you want is blue. What you don't want is red. And this is just naturally occurring from the composition of where you live, right? And it's actually broken down by county. So if you want to, this is from the United States Geological Survey. You can just Google USGS radon map. That's where it's from. You can look up your specific county. So I think we're okay where we are. We're okay. It's pretty low. This is pico, right? This is picocuries per liter. And then nuclear medicine, right? Imaging also is going to involve radioisotopes. So all your scans and all that good stuff. I don't pretend to be an expert on radio diagnostic imaging, but just so you know, if you're interested in being a radiologist, right? These are some of the isotopes you'll be working with. PET scans, and this one's using technetium. Oh, that's nice, before and after exercise. That's a picture from your textbook. And let's see, these are thyroid scans. Cool. Right. DNA mapping is something, that was where I was working. That was why I was wearing a dosimeter. Because when you are studying, if you take biochemistry, you'll learn a lot about this. You can make a DNA fingerprint using radioactive isotopes. So that's where I was exposed to. that's where we're going to stop for today. And I will see you on Wednesday.